All right, well, welcome back. So in the last video, we started to talk about the integration of rational functions by using a technique called partial fractions. So in a way, the partial fractions would actually work is that if you have a rational function that can be broken up into two fractions. So say, for example, you have this rational function and you want to break it up into separate fractions by itself. See that in the denominator, they have their own linear terms. So that is the process of uh, partial fraction decomposition. So we started by having a look at, well, how does one actually create a rational function from a sum of partial fractions? So we would just basically have to find a common denominator between the two terms, and then we would just have to simplify to obtain the rational function. And then we started to have a look at how do we actually integrate rational functions by partial fractions. So for example, if we started with this, we could break it up into these two terms here, and then we would just have to integrate each of the terms here, right? So these were the steps that we had to have a look at. And we did one example here where we had a look at where the denominator is a product of distinct linear factors, meaning that all of the factors in the denominator have degree 1. So each of them have a power of 1, 1, 1. So meaning that they would have three different linear factors. So this is one linear term, this is another linear term, and this one's also a linear term. So that was the example we had to look at last time. So now let's have a look at the second example where this time we'll have a look at where the denominator is a product of linear factors, but where some of them are actually repeated. All right. So we want to break this up into partial fractions. That's the first thing that we should always do. Well, and in this case, since we have that the degree of the numerator is greater than the degree of the denominator, so that means we have to apply long division, right? Okay, so let's start by doing the long division. So we're gonna put the terms, so we have x cubed minus x squared minus x plus 1, and we're gonna divide it by x4 minus or plus 0x cubed. So just remember to have this placeholder here, minus 2x squared plus 4x plus 1. So we applied the long division techniques that we have learned previously. So how many times that x cubed goes into x4, that goes in x times. So we're going to say it goes x times. And so if we multiply everything here and put it here, so we have subtract, well, x to the 4 minus x cubed minus x squared and plus x. And if we divide all this, we see that, well, the x to the 4th will cancel. And then we would just have, so x cubed here, negative 2x squared plus x squared. So that's going to be negative x squared. This one's going to be 3x. And then we bring down the 1 here. So plus 1. And now how many times does x cubed go into x cubed? Well, only once. So plus 1. All right. So that means if we multiply everything out, we would just get the following. So we subtract x cubed minus x squared minus x plus 1. And we divide everything, or subtract everything. So the x cubes would cancel out, the x squares also cancel out. the 1s will cancel, and we're just left with the 4x over here. So that is the remainder, 4x. So what that means is we could rewrite the rational function up here. So let's see, we have x to the 4th minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1. So that would also equal to, well, the linear term here, x plus 1, plus the remainder divided by the denominator. So x cubed minus x squared minus x plus 1. All right. So now we want to be working with this term here. So this is the one we're going to be working with. So we work with this. All right. So note that the denominator here, we could break this up by grouping. So we have x cubed minus x squared minus x plus 1. We could write x squared, which is x minus 1, minus x minus 1. And that is equal to x squared minus 1 times x minus 1, which turns out to be x plus 1 and x minus 1 squared. All right. So because here we could break this up into x plus 1, x minus 1, and then we would just have a product term here that we could just rewrite it as this. All right. So now we would just have to write this rational function as follows. So we have 4x divided by, so we have the terms x plus 1, x minus 1 squared. So what we're going to do is whenever we have repeated factors, we're going to write this term as another term. So for example, we have one term that is going to be for the x minus 1, and we're going to have a second term that is going to be for the x minus 1 squared. So these two is important. So we have this here. So that means we have one term, we have two terms. So based on the degree here, see that we have a 2 here. That indicates how many terms we need here. So we have one term and a second term. And also note that this also has to be different than this one. All right. And then the last one is just going to be plus c divided by x plus 1. So in general, so if there are higher order repeated terms or repeated factors, then we say that an divided by x minus a to the n plus an minus 1, which is x minus a n minus 1, and you would just keep on going. So that's the general rule for the rational functions with repeated denominators here. All right. So you would just keep on descending, or maybe go ascending this way, like how I did it here, up to you. And same thing we did as we did in the previous example, we would just have to work all the way to this step here, same stuff. So what we have here is if we want a common denominator of x plus 1 times x minus 2, then the first term I'm going to multiply by x minus 1. The b here is going to be multiplied by x plus 1. And the c is going to be multiplied by x minus 1 squared. And then all of this is divided by x plus 1, x minus 1 squared. And we would just have to expand everything. So we would have ax minus a plus bx plus b plus, so cx squared minus 2cx plus c. And all this is divided by x plus 1, x minus 1 squared. All right. So, and then we would just have to group the terms again. So we would have cx squared. So we have the bx squared. Oh, okay. So I'm missing another term. Okay, so this one, where am I missing a term? Oh, yes, I'm missing an x plus 1 here. Okay, so there should be an x plus 1 here. There we go. So that's also a difference of squares now. So what I could do, rewrite this a little. So I have ax squared minus a, and everything else is the same. So bx plus b plus cx squared minus 2cx plus c. And then grouping everything together, we will just get a plus cx squared plus b minus 2c x and plus or minus a plus b plus c. All of this is divided by x plus 1, x minus 1 squared. And now we would just have to compare the coefficients. So note that our polynomial here, this is also the same as saying 0x squared plus 4x plus 0 here. So if we compare them, we need to compare the 0x squared with this a plus cx squared. We compare the 4x by the b minus 2cx and the 0 with the negative a plus b plus c. So we once again compare the coefficients. And so what we then have is for the first equation, we have a plus c equal to 0. So that's equation 1. Second equation, I'll separate this. So that means we would have b minus 2c. This is equal to 4. Let me group them. All right. And then the last one, we have minus a plus b plus c equal to 0. And we'll call this equation 1, equation 2, equation 3. So I'll add an extra page here. Okay, so from here, we're going to be subtracting the following. So first, let's subtract the second equation. No, the first and the third equation. So let's go ahead. Or we could do the second and third equation and see what we get. So let's say we do 2 subtract 3. Then we would get the equation. So we have a. So the b's would then cancel if we subtract them. And we would have negative 2c minus c. So that's going to be negative 3c here. And that is going to equal to 4. So let's call this equation 4 now. So now we're going to do equation 1 and subtract it by equation 4. So now by 1 subtract 4, we see that while the a's here are going to be canceling out with each other, and we would just have c minus negative 3c, which is then going to be 4c, which is going to equal to negative 4. So that means c is going to equal to negative 1. And so if we find the other coefficients, we could see that, well, a is going to equal to 2, or no, negative going to be 1, and that means b is going to be 2. Okay, so now what we can do now is put everything back together. So remember that the 4x, or the 2, what was the x to the 4th, So we have the x to the fourth minus 2x squared plus 4x plus 1. And all this is divided by the x plus 1, x minus 1 squared. So remember that this is equal to x plus 1 plus 4x divided by x plus 1, x minus 1 squared. So if we put back the coefficients in, so we have x plus 1 plus, so the a term was going to be 1 divided by x minus 1. And then we have a plus 2. So plus 2 divided by x minus 1 squared minus 1 divided by x plus 1. And now we would just have to integrate on both sides. So we integrate x plus 1 plus 1 divided by x minus 1 plus 2 divided by x minus 1 squared minus 1 divided by x plus 1 dx. The whole thing is d. And so we would just compute this. So we would get half x squared plus x plus the ln of x minus 1. Now for this one, note that, well, the antiderivative of this is actually going to be similar to the one if we were to differentiate or integrate x to the power negative 2. So if we integrate this, we would get a 1 divided by negative 2 plus 1, x negative 2 plus 1. So if instead of x here, we would have x minus 1. So that means this integral is going to be negative 2 x minus 1 to the power negative 1, and then minus ln of x plus 1, and then plus c, where c is the constant. So that's the second example. So this is when we have repeated linear factors. So that means we would have to apply more terms with constant numerators here. Okay, so you do the same process for most of the time. So the place that where it gets a little bit different, it's simply just going to be whenever you have to deal with the partial fractions part, determining the coefficients, and working to build this part would be the same. And it just be the comparing coefficients that's going to be the same as well. So it's just building this part over here that's probably going to be most tricky. So just be a little bit careful of that. All right. So let's have a look at the third one. So let's say that the denominator contains irreducible quadratic factors in which none of them are repeated. So one important integral that we had to look at before was this one. So we had the integral of 1 divided by x squared plus a squared dx. We found that this integral was equal to 1 divided by a tan inverse of x divided by a plus c. So this integral will actually be playing an important role here, and the following example will show that. Okay, so for the integral here, let's first have a look at the rational function. So we had 2x squared plus x plus 2. And in the denominator, we have x cubed plus 2x. So note that we could common factor out the x in the denominator, and we would see that. So we had 2x squared plus x plus 2 divided by x times x squared plus 2. Now this term over here is an irreducible quadratic factor because you cannot break it up into linear factors. So what do we do here? So I'm going to label this actually. So this here is your irreducible quadratic factor. So in this case, what we're going to do is, so we're going to still break them up into linear terms. So we're still going to have an A. So for the first one, that's going to put this as A divided by X. But as for the second one, I'm actually going to be write the second term as bx plus c divided by x squared plus 2. So whenever you have an irreducible quadratic factor, you need to have this linear term that is going to be in the denominator. So we always have the linear factor, some form maybe like ax plus b, whenever you have an irreducible quadratic factor. All right. So same steps here. So we would then just have to compare the coefficients. So I'm going to find a common denominator. So we have a times x squared plus 2 plus x times bx plus c. So, and this is divided by x times x squared plus 2. So expanding everything, we have ax squared plus 2a plus bx squared plus cx. All this is divided by x times x squared plus 2. And so that is equal to a plus b x squared plus cx and then plus 2a. And then we have x squared plus 2. All right, so now we just compare the coefficients as we did before. So this one, we have a plus b x squared, and we have 2x squared, so we compare that. We have the cx, we compare with this x, and then the 2a, we compare with this 2. All right, so let's put that into a system. So we have, so comparing the coefficients once again. So we have the first one, we have a plus b. That is equal to 2. And then we have c, which is already given. So we know one of the terms is going to be 1. And then the 2a is going to equal to 2. So because 2a is equal to 2, so that means a is going to equal to 1. So we have c is equal to 1, a is equal to 1. So that means b would also have to equal to 1 then. So this one's an easy system to solve. So that means if we put everything back into the integral, so we have the integral of the original one. So we have 2x squared plus x plus 2. All this is divided by x plus 2. No, x times x squared plus 2 dx. And then this is equal to the integral. So the first term we have was the a divided by x. So that's going to be 1 divided by x times dx. And then the second term, we would have the linear term. So bx plus c is going to be the x plus 1 divided by x squared plus 2 dx, which we could also separate this into two other terms. So we have one term that is going to be x divided by x squared plus 2 dx. The second one we could have with 1 divided by x squared plus 2 dx. So the first and third term, we could use the integrals that we know. So the first one we know is going to be the ln of x. The second term, I'll leave it for now. But for the third term, we're going to have using the identity that I wrote down. So in place of a, we're going to have the square root of 2. So that means we're going to have 1 divided by square root of 2 tan inverse of x divided by square root of 2 plus c. As for the second integral here, we're going to be using some substitution here. So remember that, well, if we let u equal to x squared plus 2, then du is 2u or 2x dx. So that means x dx is going to be half of du. So that means the denominator is going to be u. So that means the integral of that is going to be ln of u. So let me write this down. So we have half divided by u du, half of ln of u, and that is then going to equal to half ln x squared plus 2. All right, so that's the integral for the second. So we have plus 1/2 ln x squared plus 2. All right, so that was it for this third example. Okay, so let's have a look at the last example, where this time we have repeated irreducible factors. So before we had a look at the non-irreducible factor, or the irreducible factor, but only for one term. The next one we're actually going to be having a look at ones that are actually repeated. So same thing as what we did in example, this example here. We had to write more terms for higher order repeated factors. So we're going to do something similar here. But instead of just having the constant term divided by x minus a to the n, we're actually going to be having ax plus b divided by the irreducible factor plus cx plus d divided by the irreducible factor squared, and so on. So what I mean is we would have to write, so a1x plus b1 divided by x squared plus a. So say that's the non-reducible factor. Then we would have a2 plus, or x plus b2 divided by x squared plus a squared, and so on. So that's what we're going to do here. Okay, so let's have a look at the first one. So we already have the factors, so let's write this as this rational function. So we have 1 minus x plus 2x squared minus x cubed divided by x times x squared plus 1 squared. So that means we're going to have, so the first term is just going to be the a divided by x, nothing too difficult for the first one. So for the second one, we're actually going to write, so using this sort of method up here, we're going to write this as bx plus c divided by x squared plus 1, and then plus dx plus e divided by x squared plus 1 squared. So both of these terms are contain non-irreducible quadratic factors. So that means we would have to use the linear term on the numerator. All right. So same thing here. We would just have to compare the coefficients. So let's find the common denominator. So for the first term, we will have the a times x squared plus 1 squared. For the second term, we would have the bx plus c times x squared plus 1. And then as for the third one, we would have x multiplied by dx plus e. All of this is divided by x times x squared plus 1 squared. So now just expanding this, so we would have ax squared plus 2ax plus a for the first one. So this second one will have x cubed plus x. So let me just go ahead and use the FOIL method. So we would have bx to the fourth plus b times x squared plus cx cubed plus cx. Yep. And then as for the third one, we will have dx squared plus e. Now, although this looks like a lot to clean up, we should be careful around here. All right, so let's compare the coefficients here. Now, am I missing any terms? Okay, so this one should be fourth. This one should be squared, and this one should just be as is, a. Yep. So let's group them together. So we have the a to the fourth and a to the fourth and b to the fourth. So let's put those together. So that is, you have this term, and we also have this term. So let's group them. So we have a plus b, x to the fourth, plus, so let's see if we have any x cubes. We do, which is just going to be this term here. So we have cx cubed. So we have cx cubed here. And then for the third term, we'll have the 2ax squared, we have the bx squared, and we have the dx squared. So let's group those together. We have 2a plus b plus d x squared. And then for the fourth one, we would just have the cx here. Yep. So the cx here. And then the e, we have the constants a and e. So we have the a and the e. And then all of this is divided by x times x squared plus 1 squared. And now we just compare the coefficients, same thing as before. So compare coefficients. So what we have here is the following. So we have a plus b, that is equal to 0. And then we have the c, which is equal to -1. And then we have the 2a plus b plus d, which is equal to, so the x squared has 2. The cx here, so that's c. Did I make a mistake somewhere? Okay, so let me see if I expanded this. So this one's correct. So we have bx cubed, bx squared, yes. And then we have the cx cubed, and then cx here. So yeah. And then we have the c. Okay, so there should be an x here. So that's a mistake. So that's be c plus ex. And then the constant is just going to be the a. So it should change this highlight. That was c and x. So that means I want this highlight and this highlight. And then the a is just going to be by itself. So it's always good to double check to make sure that you've expanded everything correctly. Otherwise, it'll lead to some mistakes. So now we would just, so c plus e, which is equal to -1. And then we would have a, which is equal to 1. So we call this 1, 2, 3, 4, and 5. But we know two numbers already. We know what c is, we know what a is. So let's go put what we know in. So if a is equal to 1, then that means b is equal to -1. And then if c is equal to -1, then that means e is going to equal to 0. And that means d is equal to, so d here, so if a is 1, so we have 2, b is -1, subtract 1. So we have 1 here. So this gives you 1. So that means d has to equal to 1 here. Okay, so we have the 5 coefficients. So let's go ahead and put that in to the integral. So we have 1 minus x plus 2x squared minus x cubed. All this is divided by x times x squared plus 1 squared dx. So the first term was going to be the a times a divided by x. So that's going to be 1 divided by x dx. The second was going to be the bx plus c divided by x squared plus 1. So it's this one. So since b was -1, so we have negative x minus 1 dx. And then the cx plus d is the other term. So we just have x divided by x plus x squared plus 1 squared dx. And yep, that should be the integral that we have. So evaluating each integral as before. So I'm first going to separate the second integral here. So you have 1 divided by x dx plus the first, so negative divided by x squared plus 1 dx minus the integral of 1 divided by x squared plus 1 dx, and then plus the integral of x divided by x squared plus 1 squared dx. Okay, so that means the integral that we get, or as a result, the first integral will get ln of x. The second integral, if you do a u substitution, this looks like the one that we did in the previous example. So instead of the x squared plus 2, we're going to have x squared plus 1. So we have half ln x squared plus 1. The third one, this is going to be the tan inverse one. So we have negative tan inverse of x. And as for the third one, if we do the repeated integrate, the repeated one, it would look something like this integral here. So that's going to be negative x squared plus 2. So we get negative x squared plus 1 to the power -1. And then plus c. So that is the last part of the irreducible or rational functions using integration of rational functions using partial fractions here. Okay, so the first example that we covered here was the one where we had all distinct linear factors. All right. The second one is where we had repeated linear factors. And then as for the third one, we had to look at where we had irreducible quadratic factors. So that way we would actually have to write a linear term on the top and the irreducible quadratic factor on the bottom. And then as for the last one, we had a look where we had repeated irreducible quadratic factors. So those are the 4 cases for integration of rational functions. Okay, so let's have a look at this quick section on rationalizing substitutions. So sometimes when we're integrating a rational function that contains an expression of the form the nth root of f of x, so sometimes it is convenient to make a substitution for the root function here. So let's say we want to integrate this function here. So we have the integral of x, the square root of x plus 4, all this divided by x, dx. So that means we're going to let u, so according to this definition, we're going to let u be the function under the square root. So let u be the square root of x plus 4. So that means u squared is going to be x plus 4 And that also means that x is going to be u squared minus 4. Okay, so that means du here, or actually I'm going to use the du from here. So that means 2u du, by taking the derivative on both sides, we get d of x. Okay, so let's go ahead and put everything into the integral. So we have the integral of the square root of x plus 4, which then becomes u, divided by the x, which is now going to be u squared minus 4. And then we have the 2u du as the dx. And so if we simplify things, we get 2u squared divided by u squared minus 4 du. So we're dealing with a rational function once again. So that means immediately we should be using partial fractions. So note that here, 2u squared divided by u squared minus 4 is equal to, well, 2u squared, u plus 2, and u minus 2. Or that is equal to sum a divided by u plus 2, and then plus sum b divided by u minus 2. So we compare the coefficients once again. So first one, we have a times u minus 2 plus b u plus 2. All this is divided by u plus 2, u minus 2, which then equals to au minus 2 ba plus bu plus 2b. All this divided by u plus 2, u minus 2. So we would have a plus b equal times u, and then plus minus 2a plus 2b. All this is divided by u plus 2, u minus 2. So we compare the coefficients. So we see we don't have an x squared here. So that means we would have, okay, so we also see that we could rewrite this rational function. So instead here, I could write this as the integral from 1 minus 4 divided by u squared minus 4. So du. So we work with this rational function here. So that's by making the division of u minus 4, or 2u squared, divided by u squared minus 4. So if we see that how many times u squared goes into 2u squared, we see that 2 times. Or, yeah. So 2 times. So we get negative 2u squared, which is equal to 0. So that means we could write this as 2 and then minus this expression here. Oh, sorry. No. It's going to be the other way around. So we have 2u squared, and we have u squared minus 4. So that's going to be twice, or how many times the 2x squared, 2u squared goes into u squared, half u squared times u. So that's subtract u squared, and then how many times does 2u squared? Oops. Yep. And that'd be minus 0. Yeah, so that's all for this one. So we would just have 0 here, and we have just plus 4. So this is the remainder here. So that would go on top here, and we just do 1/2 here. So we work with this part. So we do the same stuff here. So this becomes a 4. And then we compare the coefficients. So we first have a plus b, which is equal to 0. And we have negative 2a plus 2b to be equal to 4. Okay, so that means b is equal to minus a. And so that means we have 4a. Oh, sorry. Okay. So what that means. Okay, so some small change. So let's redo this example. So I made a small mistake. Okay, so we're still going to be letting u be the square root of x plus 4. So that means u squared is equal to x plus 4. And so that means 2u du is just going to be the dx. So that won't change. So now what I'm going to do, so that means x is equal to u squared minus 4. I'm going to rewrite this as the integral of 2u squared divided by u squared minus 4 du. So I'm going to take out the 2, put the u squared on the outside, u squared minus 4 du. And now I'm going to divide the numerator by the denominator. So if I apply the long division, so u squared divided by the u squared minus 4. So I'm going to do here is, so how many times does or no, it should be the other way. Times the u squared. So it goes into the u squared once. So that means I would just have subtract u squared minus 4, which then just equals to 4 because the u squares would cancel out. All right. So that means I could write the expression that I've written down as follows. Did I divide this correctly? Yes. Okay. So that means 2. So that I'll have the 2 here multiplied by the integral of 1 plus 4 divided by u squared minus 4. So if I actually try to find the common denominator here, so that's going to be the u squared minus 4 plus 4. So yes, I've done it correctly. And so I'm going to be working with this part here. So we would have 4 divided by u squared minus 4, which then would just be by partial fractions, u minus 2, b divided by u plus 2. So find the common denominator. We would have a u plus 2 plus b u minus 2 divided by u minus 2 u plus 2. So that would be a plus b times u plus 2a minus 2b all divided by u minus 2 u plus 2. So now I'm going to compare the coefficients so that here we have a plus b is equal to 0, 2a minus 2b is equal to 4. So if I do b is equal to minus a, so that means 4a, which is equal to 4. So that means a is equal to 1. And so that also means b is equal to negative 1. So now I will just have the integral. So the integral here I have, so 2, 1 plus 1 divided by u minus 2 minus 1 divided by u plus 2. All this du. Okay, now here this would just be equal to 2, uh, 2u, and then we would have plus 2 ln u minus 2, and then minus 2 ln u plus 2 plus c. Yep. So now I'm gonna substitute u back in. So we have 2 times the square root of x plus 4 plus 2 ln of the root x plus 4 minus 2 and minus 2 ln of the root x plus 4 plus 2 plus c. So that was basically it. I do apologize for the confusion here. So it was mainly the fact that we actually need to bring out the 2 out here before we actually go ahead and divide everything here. All right. So let's, so the next set of pages, or so this section, so we finished the techniques of integration. So now we're going to be going on to the strategies of integration here. So far that we covered the basics of integration, techniques of integration, and we have used them in all 5 sections. So we had a look at the substitution, looked at the integration by parts. We had a look at the trigonometric integrals and substitutions, and we also had a look at the partial fractions as the last one. So sometimes it's important to recall the important techniques for a given integral. But since there's no definite method to integrate, sometimes we could use some strategies when we're facing with the integral. So sometimes we'll come across a integral that might be hard at first, but we could make some ways to make it easy. So for example, the first step would be if we want to evaluate, although this may look tricky at first, it doesn't, because if we just go ahead and expand this, we would have sine squared of x minus 1 dx. And so we could also write that, well, sine squared of x is one of the half angle identities. So we have 1/2 1 minus cos 2x, right? So that means the integral of 1 minus, or 1/2 1 plus cos, or 1 minus cos 2 theta, or 2x here, I mean, minus 1 dx. And then you would just have to continue on from here, right? So next is sometimes to see if you can find an obvious u substitution for. So if the u substitution does not work, try the other techniques that we have talked about, whether it be integration by parts, trig substitution, trig integral, or partial fractions. And so sometimes you'll have to use multiple techniques. Sometimes you'll have to do maybe like a substitution and then partial fractions, which we have seen up here. And that would be the way to solve the integral. So it is not always obvious what technique you should use. So that's why the practice, if you practice integrating, you should be able to understand the concepts a little bit better. All right. So before we actually move on with the next concept, let's have a look at some practice examples. Okay. So this next part is where I'm going to practice some integrating rational, using the techniques of integration to practice. Okay. So for example, let's integrate the following. All right. So For the first one, we have the integral of x squared divided by a squared minus x squared to the power 3 over 2 dx. Okay, so this actually comes from one of our trig substitution um, formulas. So what it looks like here is that we need to be using the table that I have made, this table here. So it looks like we're going to be using a substitution x is equal to a sine theta, right? Okay, so let me go back to this page. So I'm going to say, well, let's let x be equal to a sine theta. So what that means here is that, well, if we construct a right angle triangle like this, so that means, so if this is theta, then we have the opposite being the x, a being the hypotenuse, and the adjacent being a squared minus x squared, right? Okay, so we're going to use the same method as we've done before. So we're going to say, well, if we want the denominator to be a squared minus x squared, we could use the fact that, well, the the sine or the cosine is going to be the adjacent divided by the hypotenuse. So we would have that. So cos theta is equal to the square root of a squared minus x squared divided by a. So that means a, or the square root of a squared minus x squared, is going to equal to a cos theta. And then if we cube both sides, so take this to the third power, we would have a cube here and we have a cube here. And next, similarly, well, we need to find our dx, which is just going to be a cos theta d theta. So we have a cos theta d theta. Now putting everything in, so we know that x we're going to let be a sine squared, or a squared sine squared theta. So over here we have, so a squared sine squared theta. And then in the denominator, well, since we said, well, this, the square root of a squared minus x squared all to the power 3 is going to be a cube cos cube theta. So you have a cube cos cube theta. And the dx we said was going to be a cos theta d theta. So now what we have is, so we have the integral. So this cancels. We saw 1. And this would also cancel as well. And this cos would also cancel for 1. So what we're just left with now is just sine squared theta divided by cos squared theta d theta, which is just going to be our tan ratio. So that's going to be tan squared theta d theta. But this is also equal to the integral of secant squared theta minus 1 by the Pythagorean identity. And then we could just take the integral of each term, which will be tan theta minus theta. So tan theta, according to our triangle, is just going to be opposite, which is x, divided by the adjacent, which is the square root of a squared minus x squared. So that means, let's see, this is equal to the square, or x, divided by the square root of a squared minus x squared.
minus theta, which is going to be sine inverse of x divided by a, and then plus c. All right, so that's the first example. So for the second example, let's try to integrate this integral. We have the integral of 1 divided by the square root of 9x squared plus xx minus 8. All this dx. Okay, so the first thing that we could do here, now it might not look obvious here, but the easiest way to go around this is to complete the square of the denominator. So if you remember completing the square, so if we have 9x squared plus 6x minus 8, I'm going to take the first two terms. So we have 9 bracket x squared plus 2 over 3 x, and then minus 8 out here. And then I'm going to add and subtract the middle term divided by 2, so that's going to be 1/3, and then square the whole thing. So I have to add and I have to subtract it. So that means here I have 9x squared plus 2 over 3x plus 1 over 3 squared minus 1 over 9 times 1 over 3 squared, and then minus 8. So this actually turns out to be equal to 9. So the inner part here is going to be difference of square, or a perfect square trinomial. So this is equal to x plus 1 over 3 squared. And then the constant on the outside is just going to be negative 9. So we have this term. So let's go ahead and put that in. So this integral here, we have integral 1 divided by the square root of 9 x plus 1/3 squared minus 9. And this is with respect to x. So now I'm going to make a substitution here. I'm going to say first, let u be equal to x plus 1/3 squared. Or just the 1 plus 1/3, x plus 1/3. Then I'm going to say, well, du is just going to be dx. And that's all. Okay, so now we could just go ahead and put that back in. So we have the integral 1 divided by the square root 9u squared minus 9. And this is going to be du. Then we have the integral. We could take out the 9 out here. So this is just going to be 1 over 3. So that I'll bring the constant outside. Times the integral of 1 divided by the square root of u squared minus 1. Yeah, okay, that's fine. Du. All right, so now we're going to make a substitution here once again. So this is another trig substitution. So if we consider a right angle triangle, where we would have, so let's go back to our table. So we have the x squared minus a squared. So we have u squared minus. So that means we're going to make a substitution for x is equal to secant theta. So let's go back. So we're going to say, well, let x or let u be secant theta, or du is going to be secant theta tan theta d theta. All right. So secant theta is the hypotenuse, which is u, divided by the adjacent, which is 1. So that means this length is going to be u squared minus 1. All right. So now that means if we consider the tan ratio, so that means tan theta is just going to be the square root of u squared minus 1, right? So let's go ahead and put that in. So we have this information down here. We have the du. So let's go ahead and put everything else in. So we have 1/3 times the integral of 1 divided by tan theta multiplied by secant theta tan theta d theta. So we see that the tans will actually cancel out each other, and we would just have the 1/3 times the integral of secant theta d theta, which is an integral that we actually computed before. So if you remember this integral, it was actually 1/3 times the ln of secant theta plus tan theta. And we have the plus c out here. But let's go ahead and find the expressions. So secant theta was equal to u. So we have 1/3. We have the ln of u. Then that means tan theta has to be the square root of u squared minus 1. And then plus c. But u, we said, was going to be the x plus 1/3. So let's go ahead and put that back in. So we have 1/3 times the ln of u, which was x plus 1/3, and then plus the square root of x plus 1/3 squared minus 1, and plus c. And that is the integral for the second one here. Okay, so let's have a look at the third example here. So this is example 3. Let's say we want to integrate this one. So we have x divided by x squared minus 1. Or, yeah, let's do this one. Times dx. Okay, so once again, we have a expression that is similar to what we had in the previous example. So I'm going to let x be equal to secant theta then. So that means dx is equal to secant theta tan theta. So that means tan theta has to equal to the square root of x squared minus 1. If you construct the right angle triangle, you would see that this would be obvious. So we have this x1, this is theta, x squared minus 1. Or tan theta, no, other place. Okay. So this is x squared minus 1. This is 1. Yeah. So now let's put everything in. So we know that x is going to be equal to secant theta. And then the denominator is going to be the tan theta. Then we have secant theta, tan theta, d theta. So that means the tan theta cancel. The secant times the secant is going to be the secant squared, d theta, which is just going to be tan theta plus c. But tan theta is going to be the square root of x squared minus 1. So that is just going to be x squared minus 1 plus c. And that's all for this one. So next one, let's try two more. Say we want to integrate x to the power 3 e to the power negative 2x dx. So this one, we're going to use integration by parts because we have a product, simple function or a product of two functions where both of them are simple functions and they're easy to deal with. So we're going to use the DI method or the tabular method. So the one I'm actually going to be differentiating is going to be the x cubed. And this is going to plus rho. The one I'm integrating is going to be e to the power negative 2x. So I'm going to add some extra plus, minus, and we'll see how far we go. So differentiating x cubed for maybe 4 more times, we have 3x squared. We have 6x, then we have 6, then we have 0. And as for the second one, the integral of e to the power negative 2x is going to be negative 1/2 e negative 2x quarter e to the power negative 2x. We have negative 1/8 e negative 2x, and we have 1/16 e to the power negative 2x. All right, and then we just go diagonally. So this, this, and so that means this integral is just going to be negative x cubed over 2 e negative 2x minus 3x squared divided by 4 e negative 2x minus 6/8, or 6x divided by 8 e negative 2x minus 6/16 e to the power negative 2x. And if you want to simplify it, that's okay, but I'm just going to leave it like this. Okay, so let's have a look at one more example. Let's say for the fifth one, we want to integrate the integral of a plus ln of x, the square root of it, and we divide it by x ln of x dx. Now this one looks a little bit tricky, but the first thing that you should try, remember, is to try to substitute. So we're going to say let u be equal to ln of x. Well, why? Du, we know it's just going to be 1/x times d of x. Well, where does the 1/x come from? So we have a 1, and we have the x here. So we have the 1/x here, and we also have the dx. So that's going to become the du. Okay, so now let's see what we're doing with. So we have the integral of a plus u divided by u times du. And now we have to make another substitution. So let's say we let z be equal to the square root of a plus u. So this is the rationalizing substitution. So that means z squared is going to be a plus u. So that means 2u du is going to be du, or 2z dz is going to be du. And as well, u is equal to z squared minus a. All right. So let's have a look. Oh, okay. So here we could also rewrite our integral now. So in terms of z, we have z on the top, and we're dividing it by u, where u, or now the u is going to be the z squared minus a. Du is now going to be the 2z dz. So that means we have the integral of 2z squared divided by z squared minus a dz, which looks like the one that we actually integrated before. But instead of the 4, we have the a. Note that this is going to be a, so that means when we break this up, it has to be 2z squared divided by z plus root a, z minus root a. Now this one's going to be a little bit tricky, all right? So just be a little bit careful here. So when we divide the numerator by the denominator, note that, well, okay, I'm going to rewrite this as 2 times the integral of z squared divided by z plus a, or root a, z minus root a, and dz. So that is also equal to 2 times 1 plus a, sorry. So if I try to do the long division, so I'm going to take the z squared and I'm dividing it by z squared minus a. So it goes into it once, z squared minus a. So we just have a here. So we have a divided by z squared minus a dz. Okay. So we have the first term. So I'm going to rewrite this part, actually. What we have here is 2 times the integral of 1 plus a divided by z minus root, or z plus root a, z minus root a, and dz. Okay, so now let's work with this part here. And I'll add an extra page to this. So this integral here, or this rational function, z plus root a, z minus root a, is also equal to a divided by z plus root a plus b divided by z minus root a. And so that means, so a z minus root a plus b z plus root a. All this is divided by z plus root a, z minus root a. And so we have a z minus a root a plus bz plus b root a. All this is divided by z plus a root a, z minus root a. And group the terms, so we have a plus b times z plus minus a root a plus b root a. And same denominator. Okay, so now just to compare the coefficients, for the first one, we know that a plus b is equal to 0, so that call this equation 1. The second equation we have is minus a, root a plus b root a, which is equal to a, and that's equation 2. Or also note that if I common factor out the root a here, so I have negative a plus b is equal to a, then that means negative a plus b is equal to still root a. Okay. So now, what do we have here? Okay. So now we have a plus b is equal to root a. So let me write b is equal to a, negative a. So what that means is negative a minus a is equal to root a. So that means negative 2a is going to equal to root a. So that's a is equal to negative 1/2 root a. And so that also means that b is 1/2 root a. Okay. So now what we can write here, so I'll move the coefficients over back here. So going back to the partial fractions. So back to this step, the last step that we wrote down here. This is equal to 2 times the integral of 1. A was going to be minus 1/2 times z plus root a. Or no, a is going to go up here, and plus root a divided by 2z minus root a dz. Okay, so everything is going to work out well. So we have 2 times the integral of z minus, so that's root a divided by 2 ln z plus root a, and plus root a over 2 of ln z minus root a plus c. And so expanding, we have 2z minus root a ln z plus root a plus root a ln z minus root a plus c. And substituting back to z, we said z was going to be equal to root a plus u. So a plus u minus root a ln root a plus u plus root a, and plus root a ln root a plus u minus root a plus c. And since u was equal to ln of x, so that's just going to be 2 a plus ln of x minus root a ln root a plus ln of x plus root a plus root a ln a root a plus ln x minus root a plus c. So indeed, this was actually a pretty long integral to actually be able to integrate. So we did manage to compute this integral, although it was pretty tricky. Well, the steps that we took to get there. So we had to make a double substitution, u and z, and then be able to apply the division to obtain this rational function, compare the coefficients by partial fractions again, or apply partial fractions to this part, compare the coefficients, and then integrate, and then simplify it. And that was all for this integral here. All right. So I think that would be a good place for us to end this lesson for today. The next lesson, we will actually be starting with the improper integral. So I'll actually be moving this page to this page here so that we don't mess up. So this is the next section that we'll actually be having a look at. So if you guys have any questions about the partial fractions that we had a look at today, as well as the practice examples, just feel free to let me know in the comments down below. And anyways, I'll see you guys in the next lesson.